Another design principle is to establish a clear mapping. So who knows what this is? It's a seat control for your car. How do you work it? What parts of the seat move based on what parts of this control that you move? Well, you can, and it's pretty cool because you can actually, if you want to move the seat forward, you take the bottom part here and you just slide it forward. If you want to move it back, you push it, you pull it back. So there's a very natural mapping between what the control does and what it does in the real world. So moving the seat bottom forward in the control moves the seat bottom forward in the real world. This is a good mapping because it's very obvious what does what because everything maps nicely onto the real world. So here's kind of a case example. Suppose we're designing a stovetop burner, and we have 4 burners in a square, and we have 4 controls. Is it immediately obvious which control controls what burner? No, we would need some kind of label on here, right? And Norman makes the point, again, several times, that if a design needs a label, it's failed. Things don't need to be designed in such a, can always be designed in such a way that it's the design of the object makes it very clear what does what. So, you know, this for all I know, this control could control that burner. I don't know why it would, but it could. So let's try to make this a little better. What if we split the controls in half? Well, this is certainly better, right? This kind of makes it clear that these 2 controls control the left 2 burners, and the right 2 controls control the right 2 burners. But it's still arbitrary, because we don't know which is the front, which is the back. So again, we still need to label this. How about this? Well, this is pretty good, because now, since we've set, because the way we've placed the burners, there's a very clear ordering from left to right of the burners. So then that maps nicely onto the left and rightness of the controls. But I would think this is even better, because here we have a nice arrangement of the controls that is exactly mapped onto the arrangement of the burners. And so you can see that this is, I don't even have to think to figure out which control does what burner. It's obvious because of the mapping. And things like this seem small, but these kind of mistakes, when added up over time, become really annoying. So you want to make sure that your mapping makes sense in your design. Okay, and his last principle is to give feedback. A great example of feedback is the telephone, and I don't mean your cell phone, I mean landlines. The original phone, there's a dial tone. The reason the dial tone is a great instance of feedback is because it tells you the line's connected. There's an obvious tone that tells you, oh, okay, it's connected. If you don't hear that, that gives you a clue that the phone isn't working. And old phones actually would feed the user's own voice back into the headset, so that way they know that the pickup is working. So that way their voice actually is in fact getting transmitted. Newer cell phones tend not to do that, which maybe it's then if for some reason your voice isn't getting transmitted, it's not obvious to you because you're not getting that feedback. A poor example of feedback usually are crosswalk buttons. How many people, when they press a crosswalk button, press it a lot of times? A lot of us, right? Because it's not obvious when you press the button that something happened. I think there's a number of crosswalks in England actually that when you press the button, there's like three signs. There's like don't cross, wait, and walk. And it doesn't show wait until you press the button. So that gives you an acknowledgement that you've actually pressed the button. Okay, so does that make sense? Kind of, these are some pretty general design principles. Again, notice I didn't really mention UI specifically. Norman has, I think, a chapter on computer interfaces, and this was written back in '88 when user interfaces were really bad, so he kind of rips into computer interfaces. But these principles are pretty general. So the next thing I want to talk about are conceptual models. And one of the kind of cool things about humans is that we, without even thinking about this, we automatically make mental models of things that are complicated. Like, we're so good at this, we're not even aware that we're doing this. I should note that Norman is also a psychologist, which is kind of how he thinks about a lot of these things. And this is especially true of computer applications. Most applications are too complicated for us to know how all of it works. So we kind of build a mental model of, if I write an email, then I hit send, it goes into some mailbox into the sky, and then it gets sent into somebody else's mailbox in the sky. And that's a perfectly good mental model, because that's more or less maps onto how it actually works. And it's important, therefore, to make sure that you're going to have some mental model of how you want your application to work, And therefore, you want to encourage your user to form the same mental model, because if they have a mental model that's different than the one you intended, using the application is going to be unintuitive to them, because they're going to try something and not understand why it doesn't work, because their model of how it works is wrong. And so if you make the mental model, if you design your application in such a way that users are convinced of the mental model you want, it'll be easier for them to use your application. And so here's kind of a graphic that he came up with. So you have a model to design. You make your system, whatever it happens to be, a teapot, or an application or whatever. And you can create the system, but there's no feedback from the system to you, and more importantly, there's no feedback from the user to you. The user only has interaction with the system. So you want to make sure that the system projects the mental model that you want, because then the user will be able to figure out why things are working the way they're working, because the way they expect it to work is the way it actually works. And one trick we can use for this is something that Norman identifies as affordances, which he calls the perceived and actual properties of something, especially those that determine how it could be used. For example, knobs afford turning, buttons afford pushing, we can see through glass. There are also some more obvious ones, like glass can be broken, that you kind of have to learn from experience of hitting the glass, but there are others that are more obvious. And if we can exploit affordances, then it makes it more obvious how things work, because we already have a mental model of how some of these things work, so we can just borrow those and use those to get our ideas to work. So what about this thing on the left here? What affordances does this have? Yeah, it's a door handle. Some affordances I can see is that there's this handle for you to hold on to. Does this handle afford pushing? Why doesn't it afford pushing? There's this gap behind it for you to put your fingers. It affords you to put your fingers in the back there, so that way you can pull it out. There's also this clever little lock device that affords being slid back and forth to switch the lock. So I don't need to tell somebody how this works. It's obvious from the design how to work it, right? And it's again clear. This kind of indicates that there's a hinge here on the left, so you can tell that when I pull it, okay, I'm going to pull it toward the left a little bit. What about scissors? What affordances do scissors have? Well, here's a couple obvious ones. There's two holes. Those afford putting your fingers in them. But more subtly, one of them is bigger. One of them affords putting more fingers in than the other. And there's a lot of wrong ways you could do that, but the natural way, of course, would be to put your thumb in the small hole and everything else in the other hole. Scissors also have sharp blades for cutting, so that way scissors afford cutting. So again, the affordances give clues as to how it's supposed to work. What about screen interfaces? What do screens afford? Well, with a computer, we have the screen, we have a pointing device like a mouse, we have physical buttons, we have a keyboard, and these tend to afford touching, pointing, clicking on every pixel. Somewhat interestingly, until recent years, we haven't really exploited the fact that screens afford touching. It's mostly been we've been touching the screen indirectly through the mouse and so on, or the trackball or the trackpad. But especially with mobile space opening up, we're increasingly using the fact that screens afford touching all over the place. What about these? What do these afford? So these are some widgets stolen right from the Cocoa library. What does this top left one afford? It's a button. So what is it? It affords clicking, right? What about this one here in the middle on the left? It's a search bar, so it's going to afford putting text in there. And because we know, more than that, it's an area to put text, but we also expect it to run some sort of search on that text, right? What about this one on the bottom left? It affords being dragged back and forth. It's a slider. And we have some similar ones here on the right. The interesting thing about affordances, at least in graphical displays, is that graphic design goes a long way. So these are pretty much the same shape, but is it obvious that that's a button? Not really, right? But this is very obvious that this is a button. This is actually sort of outdated. This is a lickable 10.5 pre-Lion button. That's the term Scott Forstall came up with when he was designing the Aqua interface, was lickable. Everything's supposed to be lickable. But you can see it's got sort of this texture. It's got a little bit of a shadow, and it's shiny, so it kind of looks like it's popping out of the screen, and it looks like something you can press. Whereas this on the right is kind of a flat image, it's just some funky oval that maybe if you click on it something will happen, but it's not really obvious that something will happen when you click on it. The other thing I can't really show on the slides is when the button is pressed down, it actually inverts itself to make it look like it's been pressed in, which is another kind of affords to make it clear that it's something that's being pressed. Okay, so another thing to consider when considering a mental model, or this is something that Norman talks about again, where so the user has their mental model of how your thing works, and then there's the real world. And there's these two gulfs that he identifies the kind of how you interact with the real world, and in particular the object you're interested in. So there's this gulf of execution where I have an idea of what I want to do, and I want to make it, and I want to tell the world how to do that. And if your design is good, figuring out that mapping between what I want and what I do is pretty easy. And again, in the gulf of evaluation is, once I do something to the world, how do I determine what happened? And as a designer, it's your job to minimize these gulfs so that when I have an idea of what I want to do, it takes as few mental steps as possible to figure out how to actually go about that. And when I get a result, it should be obvious what that result was and what it means, and what it means happened. So one way we can encourage good mental models is to use what are called interface metaphors. And I sort of hinted at this earlier, but the idea is we use metaphors to take advantage of things users are already familiar with. It could be other computer interfaces, it could be other real-world objects, and hopefully, if your metaphor is chosen correctly, then the user will be able to recognize that this thing is very similar to something they've seen before, and so they know how that works, so they can just apply that to this new object and not know how it works. Apple kind of did this with the iPad. They introduced the iPhone, and then they said, okay, let's make it bigger and make an iPad. And they leveraged the fact that people knew how to use an iPhone to make the iPad work, because the kind of neat thing about the iPad is that it doesn't have very many instructions that ship in the box. They leverage the fact that you know how an iPhone works to know how an iPad works. Now the problem with metaphors is they can be bad, and I'll talk about those in a little bit. But some examples of metaphors are Keynote, which I'm using right now to show these slides, is like a slide projector. The one we're familiar with for years and years and years is the desktop metaphor. I have a desktop on my computer that's like the desktop in my office. It has a trash can, like my office has a trash can. And so that metaphor isn't perfect. Who's ejected a CD from OS X? Do you drag it to the trash? Does that make a lot of sense? When you eject a CD, do you really mean to throw it to the trash? So the desktop metaphor is not perfect, but it's been around long enough that it seems pretty good. So the problem with metaphors is if you don't choose them right, they can actually be more of a problem than if you hadn't chosen a metaphor at all. So if you choose a metaphor that's too limiting, then the user won't be able to figure out how everything else works because they only know how a certain subset of things work. It can also be too powerful. If you choose a metaphor that can do more things than your thing can do, then they'll try to do something that they think the thing they're familiar with can do, and discover that your system can't do it. The one that's a little bit more sinister is that the metaphor is not matched properly. Then they'll try to do something, and you have a similar job to do, but it's not quite the same. And so they'll think they know how it works because they know how this metaphor works, but then they try to do it and it doesn't work because it's actually different in your system. So metaphors are great if they're used properly, but you need to choose them with caution because they can be really misleading if you choose them incorrectly. So a couple of guidelines for choosing a metaphor. A good metaphor emphasizes the things that are important and ignores everything else, which should seem obvious, but when you go to choose it, there's things you can forget about. And so when you choose a metaphor, you really want to think about all the things that metaphor implies and make sure that they're all relevant to what you're doing. Because otherwise people will get confused because the metaphor doesn't match correctly. Okay, so my last sort of fairly short topic is how to design for error. And I don't mean programmer errors.